Hey guys, welcome back to my YouTube channel. This is the sixth lecture of matrices, as I have already covered the five lectures. And if you have not watched them, just watch those lectures because I have covered the important properties on that lectures, like how we can add the matrices, how we can subtract the matrices, how we can multiply them. And in this lecture, we are going to discuss some properties that are very important for the purpose of your exams, like if you are going to give the J exams or any other competitive exam, MSET or any other. So this is very important because most of the questions will asked only on the basis of the properties. So for that, to crack those questions, it's very important to at least you have to know the properties, right? So here today we are going to learn 8 properties that are very important for your exam purpose. So let's start with the property second. Actually, in the previous lecture, I have already explained the property one. This one, A adjoint A is equals to determinant of A multiplied with the identity matrix and is equals to adjoint of A then A. This property I have already discussed in the first lecture, in previous lecture, in the lecture fifth. Okay, so that's why if you have not watched the lecture 5, then just go and watch that lecture. Okay. So today we are going to start with the next property second. Okay. So here these all properties we are going to discuss today. These 8 properties. So let's start with this. So we already know that adjoint of a square matrix we can find the adjoint only of the square matrix. So the adjoint of matrix A is the transpose of the matrix formed by the cofactors of A, that is if A adjoint A is equal to A adjoint A, this property already we discussed. So adjoint of A is equals to what? The cofactor. We already discussed what is the cofactor, what is the minor. Okay, so here we are getting C11, C12, C1n. Okay, so these are the cofactors, right? So from here we are getting C21, C22, C2n. And then we are getting C and 1, C and 2, C and n. So these are the cofactors, nothing but adjoint of A. Okay, so we already discussed how we can find the adjoint matrix. So let's start with the property 2. This is the property 1. We have already discussed, so no need to discuss again. So move to the next property 2. Yeah, okay. So this is the property 2. Adjoint of A, when we are going to find the determinant of this adjoint of A, we are getting determinant of A and power n minus 1. Okay. This we need to prove, right? So how we can prove this? We can take first, we can use the property 1, this one. To find, we can use this property. Okay. So here, A adjoint of A is equals to determinant of A I, right? We know this part. So from here, we can do one thing, find the determinant of both the sides. Okay. So from here, we will get find the determinant both the sides. Like this. Okay. So from here, we already discussed the properties of determinant. So how we can open this? We will get here A determinant, determinant of adjoint of A, and that is equals to, yeah, here this is one important property. I just want to remind you to solve this question, otherwise you will face the like confusion. So I'm just going to discuss one property here. I have already discussed in the fourth lecture, but again I'm going to discuss here. See, determinant of ka is equals to k and determinant of a. This property I have discussed in the fourth lecture. So why it's happening? This k will come out this k will come out. This k is the constant quantity. So when this k come out, always come with the order of this a. If the order of a is 2, here n will become 2. If the order of a matrix is n, then it will become here n. Okay, we have already discussed in the fourth lecture this property. So we are going to use this property here. So this is the determinant A, right? And here this is the matrix I, and we know that this determinant is always having the any numbers. So we can consider as a constant quantity, as a number. Okay. So when any number comes out, it will take the power of order of the matrix. So if I having the order n, let us suppose the order of I is n. So we will get here A, this determinant of A is n, and here we are getting I. Okay. Yeah. Clear? So from here, we know that the determinant of I matrix we are getting only I, so no need to write determinant here. We can simply write I here. Okay. So from here, what we are getting? See, this A, this will come to the right hand side. So we are getting adjoint of A is equals to A and A determinant. Okay. So we can remove I, because when I will multiply with this, we are getting the same thing. Okay. We already studied about this. So from here we are getting A, determinant of A and minus 1. This will come here and get subtracted as per the divisibility rule. Okay. So from here we are getting this one. So hence we can write like this. We can write like this, adjoint of, sorry, A adjoint of A is equals to determinant of A power n minus 1. So this is the proof of this property. Okay, so have you understood what is the important thing? We have to know this property. This property is very important because we are directly using here this property. So this property is very important to understand. In the fourth lecture I have explained how we are getting this. So you just go and watch watch that lecture. Okay. So move to the next property. Yeah, next property says adjoint of A is equals to A, determinant of A power n minus 2A. Okay, that we have to prove here. So let us suppose this adjoint of A is B. We are taking this as a B. Okay, so according to the property 1, we can say B adjoint of B is equals to determinant of B I, right? So now put the value of B here, this adjoint of A. So from here we are getting adjoint of A, adjoint of B is equals to determinant of B I. That is identity. Okay. So from here, now what we can do? Yeah, replace this B also. I forgot to replace this B. Write in place of B as adjoint of A. Adjoint of A is equals to adjoint of A and I. Okay, simple. So from here, what we can do? We can multiply. Yeah, we know that the adjoint of A is equals to C. We have already proved this. Determinant of adjoint of A is equals to determinant of A and minus 1, power n minus 1. So we can use this property here, right? So in place of this, we can write like this, determinant of A and minus 1 I. Okay, is this fine? Now here, what we are getting, this right as it is, adjoint of A, adjoint of A. Okay. Now what we can do, multiply A both the sides. Okay. Multiply A both the sides. So if we are multiplying A here and multiply A here, because why we are multiplying A here? Because this is the constant, it will come out and then we can multiply A. Okay. So here, so this we know that A adjoint of A is equals to determinant of A. This is the first property. I adjoint of A is equals to determinant of A and minus 1. and this I will cancel out, or we can say it will multiply with the adjoint, it will get the same. So no need to write I again here. And now this determinant A will come to the right hand side and it will become n minus 2. Okay. So from here we are getting adjoint of A is equals to A, and this will come when this will come to the right hand side, this n minus 2, it will become n minus 2, and here it is A. So now we can say this property is also true. Okay, this is the proof of this property. Okay, move to the next property. What is the next property? Next property says if we are going to find the determinant of adjoint of A, we are getting the determinant of A raised to power n minus 1 whole square. Okay. So for that what we can do, we have already proved this property. Okay. So we can use this property to prove this one. Right. So we know that adjoint of A is equals to determinant of A n minus 1 A. Right? See this one. Here. This one is the property we have already proved n minus 2. Sorry, yeah, we have n minus 2. Okay, right? N minus 2. Now what we can do? Find the determinant both the sides. Okay, so that we have to prove. So no need to change anything in the left hand side, that we have to find, right? So it will remain as same. We have to work on the left hand side will remain same. We have to work on the right hand side only. Okay, so from here we are getting see this will come outside. Then when this will come outside, it will always come with the power of order of A. We have already discussed this one. Ka is equals to Kn A, right? So this when this will come out, it will come with the order of the matrix that is inside. So here it will. This is the constant quantity because this is the determinant. We can consider as the constant quantity. So it will come outside. So we are getting here A n minus 2 multiply with this n, because we are supposing the order of A is n. Okay, so from here we are getting this one. Okay, now after solving this, what we are getting A, so n square minus 2n, and this A will become here determinant of A will become gives us here plus 1. Okay, so from we know that the n square minus 2n plus 1 is the, when we open this n minus 1 whole square, we will get here n square minus 2n plus 1, right? So we can directly write this n minus 1 whole square. So that is equals to left hand side is equals to right hand side. So we can directly write here adjoint of A determinant is equals to this. Okay, so this is the property that we need to prove. Now move to the next property. Next property is quite easy. We can simply say that any matrix A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay. Now find the transpose of this matrix. So AP will be here. A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay. So this is the transpose of the matrix A. Okay. Now find the adjoint of this matrix. This one. So adjoint of AP is equals to C11, C11, C22, C21, C31, C C12, C22, C32, C13, C23, C33. Okay. This is the adjoint of the A transpose matrix. Now what we can do, what we have to find the transpose of the adjoint of A directly. So what we can do, we can find first the adjoint of A matrix. Okay, adjoint of A matrix will be C11, C12, C13, C21, C22, C23, C31, C32, C33. Okay. Now when we are going to find the transpose of this matrix adjoint of A, we will get the same matrix, this one. Okay, you can see C11 here, C12, C13. This row will come here in this place of this column. When we are going to find the transpose of this matrix, we will get this same. Okay. So hence we can say this is equals to this one. When we are going to find the transpose of this, sorry. When we are going to find the transpose of this, we are getting the same. Okay. Let's move to the next property. Yeah, here it says adjoint of A, B is equals to adjoint of B, adjoint of A. So let us suppose this A, B is equals to C. Okay. So when we are going to suppose C, we can use the property one. C adjoint of C is equals to determinant of C I. Okay. So from C we can replace with the AB. AB adjoint of AB is equals to ABI. Okay. So from here, what we can do, multiply adjoint A both the sides. Adjoint of A, AB, adjoint of AB is equals to, we can write like this also, A, and here this one like that. Okay. So we know that adjoint A is equals to determinant of A, I, and this B will come here. Adjoint of AB is equals to determinant of A, B, determinant of B, and I. Okay. So this determinant of A will cancel out. Okay. And this I will get multiplied with the B. We are getting the same. So no need to write I here. So from here, now what we can do, multiply adjoint B both the sides. Adjoint B both the sides. So from B, this B come here and adjoint AB, and here, oh sorry, I have forgot to write here adjoint of A. Okay. So from here we are getting B. Now multiply adjoint B also, adjoint A. So from here this will become here B I adjoint of AB is equals to B adjoint of B adjoint of A. Now this will cancel out. So from here we are getting adjoint of AB is equals to adjoint of AB is equals to adjoint of A. Let me write here. Yeah, adjoint of AB is equals to adjoint of B adjoint of A. Okay, this property we have to prove. Okay, so have you understood? Let's move to the next property. Yeah, so this is the adjoint AM. So we can use this property to prove this property. Okay, so we know that adjoint of A, let us suppose A and A, okay, 2. So we can write like this, adjoint of A, adjoint of A. Using the previous property, in place of B, we are taking A, okay. So from here we can say adjoint of A square is equals to adjoint of A whole square. So in place of 2, we can take as a M also, A M is equals to adjoint of A M. So this is easy one. Okay, next property is adjoint of Ka is equals to Kn minus 1 adjoint of A. So how we can prove this one? Yeah. Okay, so adjoint of Ka is equals to Kn minus 1. So we can use this property as a proof for like we can take, yeah, we can take K as a C. Okay. So while we are taking C, we can use the property same as a, yeah. We can take the first property. We can take the first property. It will easy to prove. Okay. So from here we can say C adjoint of C is equals to determinant of C I. Okay. So replace this C with the Ka. So from here we are getting Ka adjoint of Ka is equals to Ka and this I. Okay. Now that this value we have to find only. Okay. So from here we can say Ka adjoint Ka is equal to this K will come outside and it will become Kn, and here we get A and I. Okay. So we know that and this K will come this side, it will become like A adjoint of Ka is equals to Kn minus 1. This K will become here, this K will come to the right hand side, it will become mix of K minus Kn minus 1 power n minus 1 and determinant of A. No need to write I again. So from here multiply both the sides adjoint of A. Okay. Multiply both the sides adjoint of A. Adjoint of A. Why we are multiplying after this? Because this is the constant. So that's why we are multiplying with the after constant. So from here we are getting this determinant of I, determinant of A and then I and then adjoint of Ka is equals to K n minus 1. So from here we are getting adjoint of A. So this will cancel out. I will goes with the adjoint of K. So from here we are getting the final proof. Ka is equals to K n minus 1 and adjoint of A. Okay, this is the proof of this property. It is also easy. We are using simply first property to prove this one. Okay. Now move to the question. We are going to solve 3 questions also on the basis of these properties. So first question is, if P matrix is given to us, is the adjoint of 3 cross 3 matrix A? So there is no need to write P. Instead of P we can write adjoint of matrix A. Adjoint of matrix A. So we can write like this also, adjoint of matrix A is equals to 1, 1, 2, alpha, 3, 4, 3, 3, 4 like this. Okay. Now what we can do, find the determinant of this adjoint of A. So that is equals to determinant of A n minus 1. We have already studied this property. See this one, this one. Adjoint of A is equals to determinant of adjoint of A is equals to determinant of A power n minus 1. So we are going to use this property here. See, we can solve this question with the property, with the help of property easily. So what we are getting here, yeah, find the determinant of this matrix 1, 1, 2, alpha, 3, 4, 3, 3, 4, and here determinant of A is already given to us 4. So 4, and the matrix is of 3 cross 3, so order will be n in place of n. We are getting 3. 3 minus 1 is 2. Okay, so 4 times 4 will be 16. So we have to compare with the 16. Now we can open this one. So when we are going to open, what we are getting? Let me write here. So 1, 12 minus 12 minus alpha 4 minus 6, then plus 3, 4 minus 6. Okay, that is equals to 16. So from here we are getting this one will become 0, and here we are getting minus plus 2 alpha. Okay, and here we are getting minus 6 is equal to 16. So from here we are getting 2 alpha is equals to 22 and alpha is equals to 11. So option B is the correct answer. Okay. Let's move to the next question. Statement 1 is saying adjoint of A is equals to A, and the matrix is 2 cross 2. So here we can see adjoint of A, this property, this property. So if we put a play in place of n is equals to 2, we can use here this property. Let me write here. The adjoint of A is equals to A determinant n minus 2 and here A. Okay. So in place of n, when we write 2, 2 minus 2 will give us 0, and we already know if we having power 0, we are getting 1. Okay. So this will become 1. So from here we can say this statement is true. So adjoint of A is equals to A. Okay, so this statement is true, and the second statement is also true because we can use this property. Adjoint of A is equals to A and minus 1. So 2 minus 1 is 1. So we are getting 2 minus 2. Let me write 2 minus 2. We are getting 1. So we can say this statement is also true. So according to the option, we can say option 1 is the correct answer because statement 1 is true, statement 2 is true, but statement 2 is not the correct explanation of statement 1 because we are not using that statement to prove the second one. Okay. Move to the next question. This one is a good question. It will take bit time also to solve it. So let K be a positive real numbers and let A matrix is given, B matrix is given, and determinant of A plus determinant of B is equals to 10 raised to power 6. Okay, this is given to us. Wait, determinant of adjoint of A here. Okay, yeah, determinant of adjoint of A. Okay, so what we can do, we can see this is the skew symmetric matrix, right? This is the skew symmetric matrix. See, 0, 0, 0, and here this is the negative of this, and this is the negative of this, and here this is the negative of this. So we know that the determinant of skew symmetric matrix is always getting the 0, right? So from here we can say this matrix is we are getting as a 0. Okay. Okay. So now from here it says determinant of adjoint A plus determinant of adjoint of B is equals to 10 raised to power 16. Okay. So we know that adjoint of A is equals to determinant of A power n minus 1. So this is the 3 cross 3 matrix. So 3 minus 1 will become 2. Okay. So we can write 2 here plus determinant of B 2 is equals to 10 to the power 6. So this is equals to 0 because this the determinant of B is equals to 0, right? Determinant of B is equals to 0. So from here we are getting this is equals to 0. So now we have to solve this part only. Determinant of this square is equals to 10 raised to power 6. So what we can do here, write the matrix A. Matrix A is here. So first we can find the determinant. 2k minus 1, 2k minus 1, 2 root k, 2 root k. So determinant, put the symbol of determinant only. And here next row is 2 root k 1 minus 2k root k 2 root k minus 1 k okay 2 root k 2 root k plus 1 minus 2k. This is plus 1. And the next row is minus 2 root k 2k minus 1. 2k minus 1. Okay. So what we can do, we can apply column 2 minus column 3. Apply this one. Subtract this column 3 from this column 2. Okay. So from here we are getting 2k minus 1, 0. First write the column 1 as it is. So from here this will subtract. So here we are getting 2k plus 1, 2k plus 1. Okay. 2 root k minus 1. Okay. Move to the next slide. Okay, so from here we are getting now next we can apply first write the like determinant. Okay, 2k minus 1, 2 root k minus 2 root k 0, 2k plus 1, 2k plus 1, then 2 root k minus 2 root k and then minus 1. Okay. Now what we can apply? Subtract this row third from row 2. Okay. So from here we are getting 2k minus 1. Write row 1 as it is, 2 root k, and then subtract this one. So from here what we are getting 4 root k. This will become 0 minus 2 root k plus 1, and write this row as it is. Minus 1. Okay. So what we can do now, we can open this determinant along this column 2. Okay. So we are going to take again new slide. So what we are getting here when we are going to open, let me write directly here, 0 0 0. So 2k plus 1. See this one here. This one is here, third row, second column. So we are getting with the negative sign, plus minus plus minus plus minus plus minus. Okay, so we are getting with the negative sign here. So next what we are getting, hide this row and then column. Let me write the matrix so it will be easy for you to understand. Okay, 2k minus 1, 4 root k minus 2 root k, 0 0, then 2k plus 1, 2 root k minus 2 root k plus 1 minus 1. Okay. Yeah. So from here I open along this. So we are getting 2k plus 1, and this will become minus here, and then hide this column and this row. We are getting 2k minus 1 multiply with the minus of 2 root k plus 1. Okay, multiply this one and then minus So after solving this, we are getting 2k plus 1, and then we are getting 4 root k. K root k. Okay, let me check. That is root k only. Okay, right. K root k. Okay, and then we are getting plus 2k, then plus 2 root k, then minus 1, minus plus 2k minus plus minus, yeah, minus, and then minus 8k. Okay. So from here we are getting this 6k, and this will become here. Uh, Something is wrong, I guess. Let me check. 4k square. Yeah, here it is must be k only. Let me check the matrix once again. 2k minus 1, 2 root k, then 2 root k, 2 root k, plus 1 minus 2k, plus 1 minus 2k, minus 2 root k, 2k, minus 1. Something calculation is mistake, I guess. Let me check. So column 2, column 3 subtracted from column 2. So 0, 2k plus 1, 2k plus 1. Okay, it will remain as it is. Okay, and then okay, move to the next part, row 1. Okay, so subtract row 3 from row 2. What we are getting? 4 root k. Okay, yeah. So here we are having 4 root k. So it will become 8k. Yeah, okay. Let me see, check again. So from here 2k minus 1, minus 2 root k. This one 2k plus 1. Okay, minus 2k plus 1. Here we are getting minus 2k plus 1. How? 2k plus 1. Okay, yeah, 2k only here. 2k plus 1. Yeah, okay, okay. Okay, here we have done mistake only. We have a 2k here, minus 2k and minus 2k, and I have written here minus 2 root k, right? This one. So here we have to remove this root only. Yeah. So then we will get the correct answer. Remove this root k. Okay. This is the mistake I have done. Let me correct. Yeah, after solving this, we are getting correct answer. Remove this root because this we don't have any root here. So from here we are getting minus 2k plus 1. So now then we can solve it. Take minus common from this, so this minus minus will become plus. No need, wait, no need to write here once, like write it later. So from here we are getting, yeah, we can open this, it will be easy for you. 2 to 4k minus 4k minus 4k square, okay, then minus 2k, okay, and then plus 2k, minus minus plus will become no, okay, plus 2k and then plus 2k and then minus 1 minus 8k, okay. So from here we are getting 2k plus 1 and then minus 4k square. This 2k plus 2k will become 4k, and this 4k and this minus 8k will gives you minus 4k and minus 1. Take minus common from this, we are getting here. Move to the next slide. Okay. So from here we are getting minus 2k plus 1 and here minus 4k square minus 4k minus 1. Okay, take minus common, so it will become plus. So 2k plus 1, and here we can see this is the formula of 2k plus 1 whole square. When you will open, you will get the same. So from here 2k square 4k square plus 1 2 4k. Yeah, this is the formula of 2k plus 1 whole square. So from here we are getting 2k plus 1 whole cube. Okay. Now we can see, move to the question. So from here we can see, yeah, determinant of A is 2k plus 1 whole square, whole cube, right? Cube. So 3 times 2 will be 6 and here 10 6. So from here we are getting 2k plus 1 is equals to 10. So from here we can say k is equals to plus 1, this will come here 9. 9 divided by 2, it will become 4.15, right? So we have to find the adjoint of M denotes the adjoint of a square matrix M, and K denotes largest integer less than or equal to K. So we have to find the largest integer. So we can say the largest integer will be 4. So the answer is 4. Okay. So this is the answer of this question, right? So I hope you have understood all the properties and these 3 questions also. So and in the next video I will cover all the rest of the parts. There is nothing much, but I will cover most of the things there also. So I hope you like this video. If you like this video, just try to share to your friends also and cover all the lectures because it is very important for your exam purpose. Okay, I hope you have a good day. Thank you.